Okay, so we can start it later. Uh, yeah. Mm, so are there questions from the last lecture? Okay, so if not, then let's just continue. So what I plan to do, as I was mentioning last time, what we will do is we will go over the quantum gases, the ideal quantum gases, talk about Fermi gas and Bose-Einstein Fermi-Dirac distribution, Bose-Einstein distribution, and Bose-Einstein condensation, etc. Okay. 1 minute. Yeah. So is there something? Give me 1 minute. Yeah. Yeah, just give me one. Okay. So the ideal Bose and Fermi gas. So let's first understand what do I mean by ideal gas. Gas, of course, we know what it is. So ideal just means that there is no interaction. So therefore, if I write down the Hamiltonian, it's just the kinetic energy. That's what ideal means. Now, what does Bose and Fermi they mean? So Bose and Fermi, they have the following property. So ideal Bose and Fermi, so these are quantum systems. Quantum, yes. So we saw in the last lecture that if you are dealing with a quantum system, then the microstate involves specifying the wave vector of the system or the wave function of the system. So if I have n particles, then the wave function of the system is a function of all the coordinates of all the particles. And they have the following symmetric property. It's just a property of it's a fact of nature that so if I have the wave function that is there in which there is one particle at one particle here and one particle there, and if I interchange their position, then I pick up a sign. Okay, so that is to say that if I have this is the wave function, and if I interchange the positions of the particles, I get this one. So these two wave functions, they differ by a sign. So either you get a plus sign or a minus sign. So if you get a minus sign, then that's the property of fermions. And if you get a plus sign, that is a property of bosons. So therefore, for fermions, What it means is that psi R1, R1, Rn is equal to psi minus of psi R1, R1, Rn, which implies psi of R1, R1, Rn that is equal to 0. So what it means is that in the case of Fermi system, you cannot have two particles occupying the same, same level. Okay. So you can think of it like this, that there are this energy, so what, okay. So the picture is the following, that the Hamiltonian is given to me. So I diagonalize the Hamiltonian, I get the energy eigenstates. And then I place the particles at these different energy levels, okay? And okay, so the notation with this one, what it means is that you have, one particle at energy level 1, one particle at energy level 2, and so on. And what this one tells me is that you cannot have more than one particle occupying the same energy level if you have fermions, and that is the uh, essence of the Pauli exclusion principle. So therefore, if I have these energy levels, for fermions, every energy level can have at most one particle or none, while for bosons, every energy level can have as many particles as you want. Okay? So this is the property which I need. So now let us do the calculation for ideal Fermi gas. So today we will deal with the ideal Fermi gas. In particles, in volume V, which I take to be a cube of length L. I can take whatever I want, because at the end of the day, I will take the thermodynamic limit, and so therefore the actual shape of the volume, it doesn't really matter. The Hamiltonian of the system is just given by summation over Ki square by twice n, I going from 1 to n. So these are non-interacting particles. So the particles, they don't talk to each other. There's no interaction between the particles. So therefore, if I look at the single particle Hamiltonian, single particle, that is just Pi square by twice n, let's say for the ith particle. So for this, the single particle system, I know that the energy levels, first of all, the energies are going to be discrete, and the energies are given by this here you must have done in quantum mechanics course. I mean, these are the energies of the single particle energy levels. So pH per square k square by twice m, where P, the momentum is just h per k, and k, since we are dealing with a cube, this vector is twice pi by L of n1, n2, n3, where n1, n2, n3, these are just integers. This we know from quantum mechanics. So this is for the single particle. So with this background, let us compute the grand canonical partition function why I work in like a grand canonical ensemble and not in microcanonical or canonical ensembles because we have already established equivalence of ensembles for short range systems and this is not at all interactive. So here of course ensembles are going to be equivalent. So it really doesn't matter which ensemble I choose to do the calculation and calculation is always done more simply if you consider the least constraint ensemble and brand canonical is the least constraint ensemble. So therefore, it is always easy to do it in that ensemble. So brand canonical partition function will be Q mu Vt e to the power beta mu n times the canonical partition function. This is the new variable z to be to the beta mu. We just introduce a new variable. Then in terms of that, this one writes as z to the power n times z of NV. So I need to first find out the canonical partition function, which is quite easy to do here. So the canonical partition function, what it would be? It would be that I have these different energy levels and I have to keep filling up those energy levels subject to the constraint that the total number of particles is equal to capital N. So therefore, what I should do is e to the power minus beta times h. So h will be what? H will be the total energy will be sum of individual particle energies. So therefore, this one will be summation over P of epsilon P in P and then summation over NP equal to 0 or 1, where epsilon P is P squared by twice n, where P is equal to h bar k. So if I substitute it here, what I get is this is equal to summation n 0 to infinity of z to the power n, but here, sorry, so there is a delta function here. If I plug this in here, what I get is I get summation over n0 to infinity, summation over np of e to the minus beta summation over p epsilon p np. Because of this delta function z to the power n, I can now write as z to the power summation over n. So if I now look at this one, there is a sum here and there is a sum here. So I can combine the two and write it as a product. So this one will be summation over n going from 0 to infinity of After substituting this formula here, m0 to infinity to the this times this. Okay, now let us evaluate this one. So now we going to that is equal to n. So therefore, if I evaluate this sum, this one will turn out to be pi of p summation over n set to the power minus beta epsilon p. This function whole to the power n. So this is quite easy to see why this is there. Because e to the minus beta epsilon p np and z to the power np, this I combine this way, and then summation over n1 into n3, that's as good as saying that you sum over np and then you pi over p. That is, you take the product over all possible values of. So if you do that, see, NP can be either 0 or 1 because we are dealing with fermions. So therefore, every energy state can have at most one particle. So therefore, this term is nothing but pi over E 1 plus Z e to the power minus beta epsilon. So we have found a very simple expression for the grand canonical partition function of a system of non-interacting fermions. Can compute a lot of other quantities knowing the canonical partition function. For example, I know that PB is equal to KBT log of the grand canonical partition function. So therefore, if I just do that, what I get is KBT log of product will be sum of log of 1 plus Z e to the power minus beta epsilon. Then what is the average number of particles? This we So this we have a formula. So this we know how to evaluate it in terms of the canonical partition function. So that formula was, if you write it down in terms of Z, that would be the Z tilde Z of log of Q mu B. Okay, so this one, right? So in the class we had written down the formula in terms of mu, but this formula you can translate into a formula in terms of Z um, by doing by using the fact that Z is equal to e to the beta mu. So the formula that I had written down in the last class was in the last class I had written down this formula. It's KBT tilde mu of log of Q of Z, sorry, mu BT. But now I'm writing this formula in terms of Z. Sorry, this is Z. Everything is Z. Because now I'm transformed to Z. So these two formula, you can go from one to the other by using the fact that Z is equal to e to the beta. I hope this is clear, right? That what I'm doing is that I'm rewriting everything in terms of this new variable, Z equal to e to the beta. So I know what log of q ZBT looks like. So if I do the differentiation, then what do I get? I get this Z to the minus beta epsilon p divided by 1 plus Z e to the power minus beta epsilon p. Is the total number of particles. Okay, the total number of particles, of course, this is a fluctuating quantity, but the total number of particles is equal to the number of particles in each of the energy level. So therefore, in average, it does this way. The average total particle number is sum of the average particle number in each of the energy levels, which is this. So therefore, if I combine these two, then I get the average number of particles in a particular energy level with energy p square by twice m. This is nothing but Z e to the power minus beta epsilon p by 1 plus Z e to the power minus beta epsilon. So we got an important expression here, which is the average number of particles in the energy level with energy epsilon p, which is p square by twice m or h bar square k square by twice m, which is nothing but c e to the power minus beta epsilon p by 1 plus z e to the power minus beta epsilon p. The next thing is what is the internal energy of the system? That is the average energy. So the average energy is very simply equal to, if the system is in the energy level P, then the energy is epsilon P, and the average number of particles in that energy level is this. So I sum over P, this gives me the internal energy or the average energy of the system. We study the system in the thermodynamic. In the average particle number goes to infinity, the volume goes to infinity such that the density of particles, that is a finite number. In this limit, we would like to see how does these different quantities look like. So in average, okay, I write down the expression for in average. So first of all, we know the following that our momentum P is equal to h bar k, where k is pi pi by L of N1, N2, N3. So which means delta k, this guy is pi by L of the N1 into N3, these are integers. So therefore, delta N1, if I want to take the differentiation of this, I get this. Because N1 and N2 and N3, they can change only by 1 unit. Therefore, if I have a summation over P, I can write it equivalently as summation over N1, N2, N3 of delta N1 but then this N1 and N3, they have nothing to do with the number of particles occupying any of the energy levels. They just refer to the three spatial directions because we are in 3 dimensions. But N1, N2, N3, these it should be delta N1, which is equal to 1, delta N2, which is equal to 1, and delta N3, which is equal to 1. But now I can substitute from here. So this would be equal to L cube by 4 pi cube of delta K1, delta K2, delta K3. Let me this thing, when I take the thermodynamic limit, this thing becomes L cube is V divided by twice pi whole cube of dk1, dk2, dk3. This substitution, now let us look at how in average it looks like. Minus beta itself p by 1 plus say e to the power minus beta epsilon p. But for p, I now do this, which is p divided by twice pi q of integration as a way to dk1, dk2, dk3. And now I write this term. So what I do is that I divide by z e to the power minus beta epsilon p. So I get 1 by z e to the power beta epsilon p plus 1. Try to evaluate this quantity. What is epsilon p? Epsilon p is equal to h bar square k square by twice. And k square is k1 square plus k2 square plus k3 square. So I see that this integrand it depends only on the length of the vector in this three-dimensional K space. It doesn't care about the orientation of the vector. So therefore, I can transform this into an integral of the following sort: v by twice by q of four pi k square dk divided by 1 by z e to the power beta h bar square k square by twice n plus 1. So k is the length of the vector, so it goes from 0 to infinity. Information of variable. I don't want to write everything in terms of k square. Instead, I want to write everything in terms of this quantity epsilon, which is h bar square k square by twice. So if I do a transformation, then of course, d epsilon is h bar square k by m dk and so on. If I transform this and rewrite it in terms of this epsilon, then what do I get? If I do this transformation, so I get this guy to be equal to 0 to infinity d epsilon times d epsilon divided by 1 by z into the power beta epsilon plus 1. Where this d epsilon is what? It's v, you have to just substitute it here. V by 4 pi square of 2m by h bar square whole to the power 3 by 2. So now let us look at this quantity. So I know that if I am at the nth energy level, pth energy level, then the average number of particles is this. So it seems as though this factor, this 1 divided by this factor, this is giving me the average number of particles at the energy level with energy epsilon. And T epsilon, G epsilon are giving me how many energy levels are there between epsilon and epsilon plus D epsilon. So this is epsilon, epsilon plus D epsilon. There are many, many energy levels. So G epsilon, D epsilon, it's me number of energy levels between epsilon and epsilon plus D epsilon. So it has a name. So this is called the density of states. how we get to this formula. So what we had was, we had this one to be equal to, yeah, summation over T, 1 divided by 1 by say d to the power beta epsilon p plus 1. And then we took the thermodynamic limit to get to this formula. Now we know how to obtain the internal energy also in the thermodynamic limit. This will be what? This will be, the original formula was like this. It was epsilon p divided by 1 by z e to the power beta epsilon p plus 1. And in the thermodynamic limit, this one becomes equal to epsilon divided by 1 by z e to the power beta epsilon plus 1. Pause for a minute and ask you your questions.
Sir, no questions.
Spectrum, we will look at the ideal Fermi gas at zero temperature. So till now we were considering any general temperature. Now we will see what happens when you have zero temperature. So this one you can write it as c to the power beta minus mu plus 1. Now, if epsilon p is less than mu, the temperature is zero. Temperature is zero means beta is close to infinity. So when epsilon p is less than mu, this is a negative number times infinity, this is zero. So therefore, when epsilon p is less than mu, then NP average is equal to 1. On the other hand, when epsilon p is larger than mu, That is to say that when this is positive, beta is infinity, so 1 by infinity is 0, which implies NP average is equal to 0. So therefore, if I draw this function NP average as a function of epsilon p, what I find is that mu sets one energy level which is such that when epsilon p is less than mu, NP average is 1, otherwise it is 0. Let us recall that mu is a function of temperature. Why mu is a function of temperature? Because mu is the fugacity, and fugacity enters into the average number of particles. And that depends on temperature, which temperature you are acting at, and which you are working with. So therefore, this chemical potential, this mu, it is a function of temperature. So what is this quantity? It seems like this is a very special energy such that all energy levels below it are occupied and all energy levels above it are unoccupied. So this is called the Fermi energy. EF, we denote it as EF, which is nothing but mu T equal to 0, which is defined such that all levels with energies below the Fermi energy are completely occupied and all energy levels above this energy are completely vacant at zero temperature. So now what we will do is we will obtain an expression for this Fermi energy. For that we need to use the formula for the average particle number and the average energy. So let's just do that. Well, we know what it is. The average was what? It was the general formula was 0 to infinity of epsilon G epsilon divided by 1 by z into the power beta epsilon plus 1. So when p is equal to 0, then of course this factor is equal to 1 if epsilon is below EF and it is 0 otherwise. So therefore, this expression becomes just equal to E minus EF of E epsilon G epsilon. So G epsilon, we know how it looks like. If I do this, I get T epsilon. G epsilon is P divided by 4 pi square of 2m by h bar square to the power 3 by 2 of epsilon to the power half. I can do this integral, and if I do this, I get this to be equal to V by 4 pi square 2m by h bar square to the power 3 by 2 of 2/3 EF to the power 3 by 2. Now if I divide both sides by V, the V factor goes away, you get 1 here. But what is this? This is the density of fermions, rho. Or let me use the symbol N. So we get a relation N 1 by 4 pi square 2m by h bar square into the power 3 by 2 of EF to the power 3 by 2 into 2/3. So if I rearrange this, I get an expression for the Fermi energy, is EF, which is h bar square 3 pi square n whole to the power 2/3 divided by n into 2 to the power 1/3. Then expression for the Fermi energy. I find out an expression for the average energy of the system that can also be written down in terms of the Fermi energy. The average energy is going to be 0 to infinity of epsilon t epsilon divided by 1 by say t to the power beta epsilon plus 1. But again, all energy levels about the Fermi energy are completely occupied, completely empty, and all energy levels below the Fermi energy are occupied. So therefore, this equation it just becomes this times G epsilon d epsilon. And G epsilon we know what it is. It is E by 4 pi square of 2m by h bar square to the power 3 by 2 of epsilon to the power half. So if I just substitute it there, what you get is this is equal to B divided by 10 pi square of 2m by h bar square whole to the power 3 by 2 of EF to the power 5 by 2. This gives me the average energy of the system in terms of the Fermi energy. Just the right dimension because this is h bar to the power 3 by 2. H bar is the dimension of energy. So EF to the power 5 by 2 by h bar to the power 3 by 2. That gives me a factor which is exactly the energy factor. Okay, so this gives me the average energy of the system. Okay, so the upshot of all this calculation is, I mean, I think it suffices if you just remember one simple fact about ideal Fermi gap is that if you consider a collection of fermions that are not interacting with one another, and if you are at zero temperature, then what happens is that you have these different energy levels, and then there are fermions on these energy levels. Remember that on one energy level, you can at most have one fermion. So, for example, two fermion is not possible. Okay, some of the energy levels may be empty. That is also fine. But what happens is that there is a particular value of energy called the Fermi energy, so that all levels below it are completely occupied and all levels above it are unoccupied. And this is contained in this diagram, the average number of particles in the energy level with momentum P and energy level P square by twice m. That this is completely occupied all the way up to PF and completely unoccupied above. This is at T equal to 0. And what happens when you increase the temperature? Then what happens is that some particles which are close to the Fermi energy, they get excited because when you how do you increase temperature? You have to transfer energy to the system. If you transfer energy to the system, let's say you increase the temperature slightly, Slightly means you give a little bit of energy. If you give a little bit of energy, the particles which are down here, far below the Fermi energy, they won't have that amount of energy to get excited into higher levels. But the ones which are close to the Fermi energy, they will get excited to higher levels. So what will happen is that this would start getting depleted and it would take a form like this. So this curve is for T greater than 0. And as you keep increasing the temperature, you will have a form like this. More and more particles near the Fermi energy and below the Fermi energy, they get excited to energy levels above the Fermi energy. So the energy levels above the Fermi energy, they start to get occupied, and the ones below, they start to get depleted. Okay? And we know what is the expression for the Fermi energy in terms of the particle density, that this is h bar square of, okay, these are some numerical factors, but there's just one dependence that one has to remember. So this is proportional to n to the power 2/3. So as you increase the fermion density, that is, as you increase the number of fermions in the system, as you increase n, Fermi energy is going to increase. Because as you try to put in more particles, of course, this level has to shift because of Fermi exclusion, maybe because of Pauli exclusion, that you cannot have more than one fermion per energy level. So when you are trying to put in more fermions into the system, the threshold above which things are unoccupied and below which things are occupied, that has to be pushed up. So which is exactly what is seen here. Fermi energy is proportional to n to the power 2/3. So as you increase the number of particles, the Fermi energy also increases. It doesn't increase linearly, but it increases slower than that. And that is because when you when you increase the temperature, then what happens is that only the energy levels near the Fermi energy, they get excited. So therefore, these are the ones that participate in any motion or any transport properties and so on. Okay, so as far as ideal Fermi gas is concerned, I mean, frankly speaking, this ideal Fermi gas is rather simple. I mean, the only thing that you have to remember is that we did the calculation within the grand canonical ensemble, simply because canonical ensemble calculation and microcanonical ensemble calculation are tougher to do. That's why we invented this grand canonical ensemble, because in grand canonical there are no constraints. The energy of the system can be anything. That's why we computed the average energy. The number of particles can be anything. That's why we computed the average particle number. So the constraints, the number of constraints that you have in the system is decreased when you go to a higher ensemble, and grand canonical is the highest ensemble that you can deal with, and that makes life a lot simpler because you can do all these integrations and summations in a much simpler way than what would have been possible if you had done them within the microcanonical ensemble, because microcanonical has a lot of constraints. Total energy has to be constrained, total particle number has to be constrained, and so on. So this simplifies the matter a lot. Okay, so there is one last comment that I make about the Fermi system. See, these are, the calculation that we did, these are for any generic fermions. Okay. Now, if you are specifically dealing with electrons, then you can, on one given energy level, you can keep 2 electrons. Why is it so? You may say, well, these are fermions. Why I can keep 2 electrons? Because electrons have an extra degree of freedom, which is the spin degree of freedom. So it may so happen that one is spin up and spin, the other one is spin down. This is allowed, no problem. What is not allowed is you cannot have 2 spin up. This is not allowed. Okay. I would say that is all that one has to know about fermion system. The only thing that we did not do is what happens when you introduce interaction among the fermions, okay? Then of course calculation becomes much more complicated, and in fact nothing can be done exactly. Landau developed this, so to say, the Fermi liquid theory to take into account the case of fermions with interactions, where he thought about some what is known as rest fermions or some quasi particles, but that theory is much more involved than this one. But for non-interacting fermions, I think this is all that one has to know in order to appreciate the physics of fermions. So let me pause for a minute and ask if you have questions on this one.
Hello, sir. Am I audible?
Yeah,
Okay, I just want to know some of the limitations of this ideal Fermi gas model, if any.
yes. Right. So one limitation is of course that this is for ideal Fermi gas. Ideal means there is no interaction. Okay, so if you recall, the Hamiltonian that we were writing had this form. So the particles are not interacting. They are fermions, but there is no potential energy term. So that is the limitation. This one applies only to a system of non-interacting fermions. If you include interaction in the system, then things become more complicated, because then of course you cannot do these integrals so easily. First of all, how do you see what we did was we said that the total energy is the sum of the single particle energy, and the single particle energy was just the kinetic energy, right? So E square by 27. So a single particle is like a free particle. So we know the energy levels of the single particle system that we have learned in quantum mechanics. So single particle, it's a free particle, h bar square k square by twice m is the energy contained in a cube, and we know that k is going to be quantized and so on. But if you have interaction, then this I cannot this epsilon p, getting this epsilon p itself is complicated, because there will be cross terms. No, I cannot just write it as sum of single particles and then find the energy levels of the single particles and add them up. I cannot do like that.
Okay. And what about the ground state energy of an ideal Fermi gas at T is equals to 0? Is it same as EF, the Fermi energy level, or it is different?
The ground state energy will be the lowest value that epsilon p can take, which is 0.
Okay.
Right? Because epsilon p is p square by twice m, and p is what, h bar k, and k can be 0. So therefore, it is 0 all the way up to EF.
Okay. Thank you, sir.
Okay.
So no more questions, sir. Thank you so much.
So, shall I now move on to, so how long am I supposed to go on?
4:30, sir.
Because we started late, no? So, okay, so maybe I go on for another 15 minutes, let's say. I do a little bit of ideal both case, and then we can continue tomorrow.
Sure, sir. Sure.
Okay. now we come to ideal Bose gas. Because in the case of Bose gas, again it is ideal, so the energy is just kinetic energy and everything will go through whatever we talked about in the case of fermions. The only difference now is that in any energy level, now you can keep as many particles as you want, because for bosons there is no exclusion process. So therefore, let us just compute the grand canonical partition function. So the grand canonical partition function will be what? This would be summation over z to the power n of z of n t in going from 0 to infinity. But then this is what? This is z to the power n, and if I write this guy would be what? This guy would be, the energy will be e to the power minus beta, again like previously, summation over epsilon p np and then you sum over all possible values of np subject to the constraint that summation over np is equal to n. Where np can now be equal to 0, 1, 2, 3, etc. With this, I can write this as summation over n equal to 0 to infinity as previously pi of p 1 plus z e to the power minus beta epsilon p to the power n. So I need to compute this this summation. So the best way to compute this summation is to take an example. So let's take an example to see what will be its form. Let us say that you have only three energy levels, 1, 2, and 3. So then this thing will be what? It would be summation n equal to 0 to infinity, summation over n1, n2, n3, such that n1 plus n2 plus n3 is equal to n. And there will be, sorry, there is no 1 plus, sorry. So there will be three such factors, z e to the power minus beta epsilon 1 n1, z e to the power minus beta epsilon 2 n2, into z to the power minus beta epsilon 3 n3. Just to expand this out, first thing is when n is equal to 0. When n is equal to 0, n1 into n3, these are number of particles. If the sum is 0, these are positive numbers, they all have to be 0. And if n1 is 0 and n2 is 0 and n3 is 0, you get something to the power 0, something to the power 0, something to the power 0, you get 1. Next, when capital N is equal to 1, then either n1 is 0 and n2, n3, n1 is 1, n2 0, n3 0, or n2 is 1, n1 0, n3 0, or n3 is 1, n1 0, n2 0. So you will get three factors. So we will get z e to the power minus beta epsilon 1 plus z e to the power minus beta epsilon 2 plus z e to the power minus beta epsilon 3. The next case is when capital N is equal to 2. So then there are 6 possibilities. either N1 is 2 and N2 0 N3 0, or N2 is 2 and N1 0 N3 0, or N3 is 2 N1 0 N2 0, or two of them are both equal to 1 and 1 is 0. Okay. So let me see what will be the corresponding terms. Term will be z to the power minus beta epsilon 1 2, or let's say z to the power minus beta epsilon 2 plus z to the power minus beta epsilon 2, or there will be cross terms of the following sort: z to the power minus beta epsilon 1, z to the power minus beta epsilon 2, or z to the power minus beta epsilon 2, z to the power minus beta epsilon 3, or z to the power minus beta epsilon 1 into z to the power minus beta epsilon 3. But if you look at these terms, we get that this is nothing but product of such factors: 1 plus z e to the power minus beta epsilon 1 plus z square e to the power minus beta epsilon 1 whole square plus dot dot dot. This is one factor, and a similar factor for 2 and a similar factor for 3. So what is this guy? 1 plus x square plus x cubed. This is nothing but 1 divided by 1 minus z e to the power minus beta epsilon 1. So therefore, we get the grand canonical partition function to be equal to pi of p 1 divided by 1 minus z e to the power minus beta epsilon. This will be true provided, of course, this factor. You see, this is a one. You can see 1 plus x square plus dot dot dot. This I wrote it as 1 by 1 minus x, provided x mod is less than 1. So therefore, this quantity has to be much smaller than 1. Not much smaller. This is true, provided z e to the power minus beta epsilon p is less than 1. Implies since z is equal to e to the power beta mu, less than e to the power beta epsilon, which implies mu has to be smaller than epsilon p. But what is epsilon? Epsilon p can have many different values, but the lowest value that it can take corresponds to the ground state of the system, which is 0. So epsilon p minimum is 0. So mu therefore has to be smaller than 0. So therefore mu has to lie in this range. Correspondingly, z will lie in this range. So therefore, this is the grand canonical partition function, and then if I compute PV by KBT, then there could be this log of Q of ZVT. But log of that quantity will be what? It would be this minus summation over P log of 1 minus a e to the power minus beta epsilon p. For a particle, which I know z till del z of log of q of zvt. So using this expression, what do I get? I get this to be equal to z e to the power minus beta epsilon p by 1 minus z e to the power minus beta epsilon p. But we know that n average is nothing but summation over p and p average, which implies I get in p average, the average number of particles in the energy level with energy p square by twice m is just z e to the power minus beta epsilon p by 1 minus z e to the power minus. Once I know the average number of particles in the energy level P, then I know the average energy will be just summation over P epsilon P in the average. Okay, so, are there questions up till now?
No questions, sir.
Okay. Yeah, so so maybe I just quickly summarize what I did today, because then tomorrow we can talk about Bose-Einstein condensation. Okay? Because that would be a good way to end the course. Okay. So let us just quickly summarize whatever we did until now. So we started off with the component on classical statistical mechanics. So that is to say that I have a classical system. It comprises very many number of particles. The system is isolated, has got a fixed number of particles and has got a fixed volume. And we asked, given this macro state, how many microstates are possible? We found that there's a huge number of microstates possible. And each of these microstates can be represented as a point in the 6n dimensional phase space of the system. So we defined this quantity called the phase space density and found that the phase space density evolves in time according to the Liouville equation. And the time evolution that we derive for the phase space density, this Liouville equation, is based on the fact that individual particles are evolving in time according to the Hamilton equations of motion. So Hamilton equations of motion for particles and Liouville equation for the phase space density. And once we know the phase space density, we know how to write down an expression for the average value of an observable. An observable, a macroscopic observable that I can measure in experiments. I can write it as the average of the observable with respect to the phase space density. Because different microstates will have different values of the observables, and when I take the average, that is equivalent to taking an average over the phase space with respect to the phase space density. Then we talked about equilibrium when the average value of an observable doesn't depend as a function of time. And we saw from Liouville equation that this happens when the phase space density Poisson commutes with the Hamiltonian. Then what we said is that okay, it has to Poisson commute with the Hamiltonian. So the simplest situation that I can think of is the case when the phase space density is uniform. It is independent of energy. Everywhere in the allowed region of the phase space density is uniform. That allowed us to define the microcanonical ensemble. And in the microcanonical ensemble, we normalize the phase space density by using this factor n gamma in VE. And gamma in VE was just the total number of consistent microstates of the system, consistent with the given microstate. Once I know gamma, then what was the next thing that we did? We took the log of it and multiplied it by Kb, and we got the entropy of the system. And we said that entropy is also a quantity that we already know from thermodynamics, is a very important quantity. And when I took the derivative of entropy with respect to energy, I get inverse temperature. Entropy derivative with respect to volume gave me pressure by temperature, and so on. So from microcanonical, we went to canonical, which is the case when the system is not isolated, but it is exchanging energy. And there we found that in equilibrium, the phase space density is given by e to the minus beta h divided by the partition function, the canonical partition function. And here, minus kBT log of the partition function gave me the Helmholtz free energy of the system. F is equal to E minus Ts. Okay, so the next thing that we talked about was the grand canonical ensemble, when the system can extend both particle and energy with the surroundings. And here the phase space density is given by e to the beta mu n minus beta h divided by the grand canonical partition function. And the grand canonical partition function, when I took the log of it and multiplied by Kb, we get the pressure times volume of the system. We found that this formalism applies also when you deal with quantum systems. The only difference is that instead of talking about a phase space, now you have to talk about density operators. You cannot define a phase space for a quantum system. But this density operator rho, it has the same evolution as in the classical case, excepting that one has to replace the Poisson bracket in the Liouville equation with a commutator with suitable factors of I and H bar. And then we saw that the quantum statistical mechanics is exactly the same as in the classical case. Whenever you have to do integrals in the classical case, now you have to do trace operation, matrix trace operation. Today, in this second lecture, what we did was we dealt with the case of an ideal Fermi gas, a collection of particles which are fermions in the sense that, first of all, they are non-interacting, that's why they are called ideal, and secondly, being fermions, no two fermions can occupy the same energy level. And we found out that for this system at zero temperature, there is one threshold energy below which all energy levels are occupied and above which everything is unoccupied. We found an exact expression for the Fermi energy in terms of the density of fermions. The last thing that we talked about is the ideal Bose gas. Again, the particles are non-interacting, but now you can have more than one particle in one energy level. And we found out the following thing. This is the grand canonical partition function for the system of bosons. This is PB by KBT. This is the average energy of the system. This is the average particle number. And this is the average number in one particular energy level. Okay, so tomorrow what we will do is we will take it up from here. Talk about a little bit more about these integrals, how do they look like when you go to a continuum, that is thermodynamic limit, and then talk about what is known as Bose-Einstein condensation. Okay, so that is roughly the plan for tomorrow, and then we will see that both the ideal Bose gas and ideal Fermi gas, both when you make the temperature very high, both start to behave identically. They have similar behavior, and the behavior allows one to define what is known as the ideal Boltzmann gas. That is the high temperature limit of the Bose gas and the Fermi gas. These are the things that we are going to cover tomorrow. So are there questions?
Sir, I have one question.
Yes.
What is the main difference between both ideal gas?
So what is the main difference between?
Both ideal gases. I mean, last two gases. I mean,
Ideal Bose gas and ideal Fermi gas?
Fermi gas. Yes.
Okay. So, okay. So it's just the following that so this is ideal Bose gas. This is ideal Fermi gas. So the main difference is that in the case of if these are the energy levels of the system, in the case of ideal Fermi gas, you cannot have more than one particle on any energy level. You cannot have two particles. This is not allowed. In the case of Bose gas, you can have as many particles as you want. This is the main difference. Okay. Does that answer your question?
Yes, sir. Okay, sir. Thank you, sir.
Okay. Are there other questions?
No, sir. Thank you, sir.
Okay then. So then, if there are no other questions, then let's continue tomorrow with Bose-Einstein condensation and ideal Boltzmann gas. Okay.
Okay, sir.
Okay then. Thank you then.